Okay, thank you everyone for coming and thank you for the invitation. So let me start by saying this talk is going to be way more technical than the previous one. So if you have any questions, feel free to interrupt me. We're happy to take any questions at any point. Okay, so the topic is how do we certify non-negativity of polynomials? Okay, so what does that mean? Let's say you're given a polynomial in n variables, x1 to xn. So right, you're taking these polynomials take real numbers and then they give out a real number. Right, so how do we certify that the polynomial is non-negative, right? What does certify mean, right? So let's say you have a polynomial and you want to convince your friend that the polynomial is indeed non-negative. How are you going to do that? Right, so how do you convince that, right? Because the polynomial takes real numbers. So if you want to list, enumerate all the real numbers, they are uncountably infinite, right? So you obviously cannot do that. So how can we answer such a question, right? So what kind of a certificate can we give? Right, so if it's like 1D or something, maybe one variable, then maybe you can plot it on a piece of paper and show, okay, look, it doesn't get there. But then that also raises some precision questions. If you're very close to zero, then is your plotting accurate enough or not? Right, there are many such questions. Right, so that's the kind of thing that we'll try to address. How do we prove the existence of a good certificate? And assuming that the answer to the first question is true, how do we compute such a certificate? Okay, so let's look at some examples. So let's say you have n is equal to 2, you have two variables. Let's say look at this polynomial, right? X1 square plus x2 square. Is this a non-negative polynomial? And how do you prove that it's a non-negative polynomial? Right, okay, so since this is over real numbers only, x1 square will always be non-negative, right? Because you're taking a square of something. And x2 square, similarly, always non-negative. So if you add two non-negative numbers, that has to be non-negative, right? So that's one certificate. Okay, so in some sense, if you have a square, which is, we know that's non-negative, even if you take a sum of squares, that is also a non-negative number. Okay, okay, let's look at this example. So it's x1 square plus x2 square plus x1, x2. Is this a non-negative polynomial? Why is that? Huh? Okay, so you can write this as x1 square divided by 2 plus x2 square divided by 2 plus x1 plus x2 whole square divided by 2. Right, so then we can use the same logic that we did in the previous example. Right, each of these summations is a square. Squares are non-negative, so sum of squares are also always non-negative. Okay, some more examples. Let's say now you have a polynomial in variables x1 through to xn and y1 through to yn. And this polynomial, is this non-negative? I guess you can say all the examples, the answer is yes. The question is why. Right, so why is this non-negative? Okay, so yeah, so if you know what the Cauchy-Schwarz inequality is, so then you know that summation over I xi yi is at most summation xi square times summation y square, the whole thing under root. Right, so this is also using the Cauchy-Schwarz inequality. This you can prove is non-negative. One more example. Okay. Is this non-negative? So here there are only two variables, x and y. Okay, good. So using using the am greater than or equal to gm, you can prove this, right? So if you take the arithmetic mean of the first three terms, right? So you know that it's greater than or equal to the geometric mean of these things. Right, so its arithmetic mean is 1 plus x to the 12 y to the 6 plus x to the 6 y to the 12 divided by 3 is greater than or equal to x to the 6 y to the 6. Right, so these are all like 4 examples that we saw where you can prove that a polynomial is non-negative without like writing down this infinitely large evaluation table, right? And right, so the question is, so how do we answer these kind of things in general? Do we just keep adding more and more tools to our toolkit, which we can use to prove non-negativity? Or can we just have one tool which will answer all of these things? Right, so the previous two, the examples we saw in the previous slide, they were both sums of squares kind of proofs, right? Here we are doing something else. But it turns out, even the first example, you don't really need Cauchy-Schwarz, right? you can actually write this as a sum of squares, right? So I'll leave this as an exercise for you to verify. This term is exactly equal to this term over here, right? And what is this now? So this is also a sum of squares, right? So xi yj minus xj yi square, each of them is a square, so it's a non-negative term. And you're summing them over all pairs, so it's again a sum of squares of polynomials, right? So this is also non-negative. And you know where this is going, right? So the next one also you can write as a sum of squares of polynomials. It's a little bit more complicated. You can either try to verify this or just take my word for it, that you can actually write this as this polynomial here, right? And again, this is non-negative. Why? Because 1 is non-negative. This is x to the 4 y square, which is a square. This is x square y to the 4, which is also a square. And each of these terms are also squares, right? So even if you open this up, it's still a sum of squares, right? So again, there's another sum of squares proof that this polynomial is indeed non-negative. Okay. So at least looking at these examples, one can ask, can every non-negative polynomial be expressed as a sum of squares? Right? Unfortunately, the answer turns out to be no. So there was a non-constructive proof by Minkowski and Hilbert from the late 19th century, which showed that there exists non-negative polynomials, which you cannot write as a sum of squares. But it took almost like 7 decades to come up with a concrete example by Motzkin in the 1960s. Right? So this polynomial is known as Motzkin's polynomial. Right? So there's 1 plus x to the 4 y square plus x square y to the 4 minus 3x square y square. Okay? Now again, there's a non-negative polynomial because using the same argument as in the previous slide. Arithmetic mean greater than or equal to geometric mean. If you take the arithmetic mean of the first 3 terms, that's equal to x square. So and the geometric mean is equal to x square y square. Okay? So it can be shown that this cannot be represented as a sum of squares of polynomials. That requires some amount of work, so I'll not go into that. But yeah, essentially it says that you cannot write this polynomial as a sum of squares, right? It requires a lot more work, right? But what you can do is you cannot write this polynomial as sum of squares, but if you multiply this by x square plus y square plus 1, that can indeed be written as a sum of squares, right? Sum of squares of polynomials. So I'll leave that as an exercise for you. It'll maybe not too hard to just play around with it and come up with the decomposition. So what does that mean now? So even if we can write this x square plus y square plus 1 times this polynomial as a sum of squares, that is still a proof of non-negativity, right? Because if you can write this as a sum of squares, what we are getting is that this product of these two things is non-negative, right? X square plus y square plus 1 is always positive, right? Because x square is non-negative, y square is non-negative, 1 is positive. So the sum is always positive, right? So if the product of these two things is non-negative, one of these terms is always positive, then the second term also has to be non-negative, right? So that's also another certificate that this polynomial is indeed non-negative. Okay. So now inspired by this, we can ask, can any non-negative polynomial be represented as a sum of squares of rational functions? Okay, so this is the Hilbert's 17th problem. Okay, yes, a little bit of history here. So Hilbert was one of the leading mathematicians from the 19th century. And in 1900, he released a list of like 23 significant open problems, or problems which he considered to be significant open problems in mathematics. And these problems have been referred to by the numbering in which he released them. And they have been highly influential in setting up the research agenda for the next 100 years since then. Okay, and the 17th question that he asked was this: can any non-negative polynomial be represented as a sum of squares of rational functions? And the answer is yes, indeed it is yes. So Hilbert or Artin proved in 1927 that this is indeed true. Okay, I'll come to that. Well, okay, by rational functions I mean just one polynomial divided by another polynomial. That's what I mean by rational function. Okay. Right. So at least, yeah. So what one can say here is that we answered the first question, right? So we said, how do you certify that a polynomial is non-negative? This question answers that, right? You can always write it as a sum of squares of rational functions. And so that is like a one-shot way of proving non-negativity. You don't need to use any more toolkits. Just one tool will suffice. Okay. Sometimes, what we saw till now was how do you prove that a polynomial is non-negative? Sometimes the complementary question of how do you prove that a polynomial is not non-negative is also very useful, right? And in computer science, especially in designing algorithms and many other things, this complementary question becomes very useful, right? Yeah, sorry. Yes. Yeah. Right. So that's the point. So it'll have to be one of those polynomials where the denominator is non-zero. That's sort of what that is implying, right? Okay. So technically, what we are saying is, um, so things will look like this, right? So you will multiply it by one polynomial times pxy, which you are writing as a sum of squares, right? So what that means is, so the denominator is what you're multiplying over here, right? So if this denominator becomes zero, then that means the other side also has to become zero. Thank you. Okay, so now we're going to look at the complementary question. How do you certify that a polynomial is not non-negative? So this is a very powerful theorem. So let us slowly unpack what this says. So till now, we were only trying to prove the non-negativity of one polynomial. Now, let's say you are given m polynomials, right? Multiple polynomials. And we want to check whether this polynomial is satisfiable or not, right? So by satisfiable, we mean, does there exist one x such that all of these inequalities are satisfied? Right? Does there exist one x such that p1x greater than equal to 0, p2x greater than equal to 0, and pmx greater than equal to 0? If there exists one such x, then we say it's satisfiable. And when we say it's unsatisfiable, that means for each x, at least one of these polynomials is strictly negative. Okay? So, right. So what this positive Stellensatz says is that if P is unsatisfiable, if and only if there exists sum of squares polynomials Q, Lx, such that this holds. -1 is equal to sum over all L of the binary strings of length M, QLX times P1x to the L1, P2x to the L2, up to PMX to the LMX. So basically, you're taking all possible subsets of these products of these polynomials and then multiplying that by a sum of squares polynomial. Okay? Okay, yeah, so let's look at how this relates to what we saw till now, right? So till now, we were only looking at one polynomial. So let's look at the special case when m is equal to 1, right? There's only one polynomial. So what does it mean for that system to be unsatisfiable? Right? So it's satisfiable if there exists a single x such that p1x is greater than equal to 0. Then we are saying it's satisfiable. So when you're saying unsatisfiable, that means for all x, p1x has to be strictly less than 0. Right? That's what unsatisfiable means. So then what does this theorem imply there? Well, m is equal to 1, so we're only going to sum over two terms here. So then -1 is equal to q0x plus q1x times p1x. Okay, so if we turn this around and write it a little differently, what we are saying is that minus p1x is equal to 1 plus q0x divided by q1x. Okay, and q0 and q1 are sum of squares polynomials, right? Right, so if p1x is strictly less than 0, then minus p1x is strictly greater than 0 for all x. So what this is implying is that you can write a positive polynomial as a sum of squares of rational functions. Sorry, was there a question? Okay, so this is the special case. So this is what this is proving is something a lot more general, right? Yeah. Yes. Right. So the actual theorem proves that, but I'm just stating it a weaker version, if you can call it that. Yeah. No, I mean, in this case, you can write it as a sum of squares, right? This is 1 plus this times q0x plus q1x. But what I showed in the previous slide was actually a rational function of sum of squares. But the theorem actually says sum of squares of rational function, so it's actually stronger. Yeah, we can do that as well. Sure. Yeah, that's also a good point. Yeah. Sorry. No, so this says is that it's a sum of squares, right? So Q0 and Q1 are sum of squares. So you can write this as 1 over Q1x plus Q0 over Q1x, right? So both of them are sum of squares of rational functions. So can you say that again? I'm going to. Yes. Right. So that's what I'm saying. So what I stated here is a slightly weaker theorem. But as Rohan pointed out, you can actually do this a little more generally, right? So let's say you multiply and divide by Q1x. So denominator becomes Q1 square x. And the numerator becomes Q1 times Q0 Q1, right? So Q1 is now a sum of squares. Q0 Q1 is also a sum of squares, right? So if you just get sum of squares of rational functions, you can also make it the other. Okay, yeah, so the special case generalizes what we saw earlier, but this is proving something a lot more stronger, right? So not just one polynomial, even if you have multiple polynomials, you can actually get some sort of like the correct sum of squares generalization of this. By the way, if you're wondering why this is called positive Stellensatz, you should ask me in the break after this. There's more history behind it. It sort of generalizes this thing called null Stellensatz, and that's where the name comes from. But if you're interested in this, please ask me after the talk during the break. I'll tell you the history. Okay, any questions about this? Shall we move on? Okay, so till now, all these certificates that we saw the Krivine, Stengel, positive Stellensatz, that only shows the existence of certificates, right? From a computer science perspective, you also need to come up with algorithms to compute such certificates. So how do we do that, right? So in particular, we want efficient algorithms to compute such certificates. So how do we measure efficiency? So the running time of an algorithm, it's basically the number of fundamental operations that an algorithm performs, right? So for example, if you want to add two numbers, so how would you do that, right? So if they are, let's say, an integer, so ideally in a computer, they are represented in binary form. So let's say they are b-bit numbers. So if you want to add two numbers, the number of fundamental binary operations that you're doing would be something like some 4 times b or something, right? Because that's the number of bit operations you're doing. Right? So the number of fundamental operations that an algorithm performs is what we call the running time. Okay? And we say an algorithm is efficient if its running time is polynomial in the size of the instance. Right? So what do we mean by size of the instance? It refers to the number of bits that are needed to store your input instance. Right? So again, so if you want to add two numbers, you're going to write them down in binary, right? So the size of the instance would be the number of bits that are needed to write down the instance, write down these two numbers. Okay. So for example, so what would be an efficient algorithm? So if you want to sort n numbers, let's say the n numbers are given in some sort of an array or something. So an algorithm which makes say 100 n log n comparisons, right, would be an efficient algorithm, right? Because the number of comparisons, let's say you take two numbers and say whether first one is bigger, second one is bigger, or both of them are equal, right? So an algorithm which makes 100 n log n comparisons would be an efficient algorithm. Whereas what would be an inefficient algorithm is, let's say you enumerate all the n factorial permutations and then look at the one which is respecting the sorted order. So that would be an inefficient algorithm, right? Because the running time of that would be n factorial, right? Which is like exponential. So that's not a polynomial. Okay, so everyone clear what an efficient algorithm is? Okay, now how do we compute these sum of squared certificates? Right, so this positive Stellensatz theorem only guarantees the existence of certificates. So the question is, how can we efficiently compute them? Or can we even compute them at all, right? So here we'll need to define this quantity called the degree of a certificate. Right, so the degree of the certificate is the largest degree in the polynomial decomposition in the sum of squares. Okay, and I'm not going to go into details, but there are some off-the-shelf algorithms that you can use to compute degree D SOS certificates, if they exist, in time that is order n to the d. Right, so there's this algorithm called semi-definite programming, which is a very big. general algorithm which one can use for this. So I'm not going to go into the details of all of these things, but perhaps we can just assume for the purpose of this talk that you can compute degree D SOS certificates in time n to the D. Okay, so if you want an efficient algorithm, your D has to be a small number, right? To use this algorithm, if it's like a small constant, then this will be a polynomial. But if you have like degree n SOS proofs, then computing them will not be a efficient algorithm. Okay, so the moral of this slide, you want, from the perspective of computation, you want small degree SOS proofs. Okay, so at least in computer science, there's a lot of interest in polynomials over the hypercube. Okay, not over the entire real set number of real numbers. So by that I mean, so hypercube is just a set of vertices 0, 1 to the n, right? So it's a set of binary strings. So we are primarily interested in polynomials which take 0, 1 values and output some real number. So these kinds of polynomials capture lots of discrete optimization problems. Okay, so let's look at some examples. So one of the very well studied problems in computer science, theoretical computer science, is to compute the maximum cut of a graph. So what does that mean? So a graph is you're given a set of vertices and a set of edges. Okay, so you can pictorially think of it like this. All these red dots here, they are the vertices. And the line segments joining any two of these dots, they are the edges. Okay, so the goal here is to compute the maximum cut. So what does a cut mean? So a cut is any partition of the vertex set, right? So any partition of s comma v minus s of the vertex set, that's what we call a cut. And okay, like, yeah, for example, if you take this to be a set of vertices, so then that is a valid cut. And you want to compute the maximum cut. So by maximum cut, we mean the cut which maximizes the number of edges which are cut. Okay, so in this, we are going to count how many red edges are there. So those are the edges which are being cut, right? Because one vertex lies on one side, the other vertex lies on the other side. So you want to find the partition which maximizes the number of edges which are cut. Okay, so that is the maximum cut problem. So now we'll show how you can capture this problem using polynomials over the hypercube. Okay, so any questions till now? What we are doing, what we are trying to do? For polynomials over the hypercube, the degree can be at most 2n. In general, it's hard to say, right? It can come up with any polynomial, right? Which has. Okay, sure. If it's some constant times the input degree, yeah. Right, yeah. So that they can prove, but then the input degree itself can be, I mean, the polynomial itself can have like very large degree, right? So I'll come to that in like a couple of slides. We'll address that question. Yeah. Okay, any other questions about this? Okay, so is the question clear what the max cut problem is? So given a graph, you want to compute a partition of the vertex set S cross V minus S so as to maximize the number of edges which are cut by this partition, right? By the edges cut, we mean the edges which have one vertex on one side, another vertex on the other side. So we'll see now how to formulate this as a polynomial non-negativity problem. Okay, so we're going to introduce a variable xi for each vertex. Right, so the variable is going to take values 0 or 1. Okay, and so let's say you assign some arbitrary values to each of these variables. Each xi either gets value 0 or value 1. And let s sub x be those vertices for which you gave the value 1. Okay, so in this example, let's say these are the set of vertices for which you gave the value 1. And these are the set of vertices for which you gave the value 0. Okay, so now fix any edge ij in this graph. Okay, so an edge ij is cut by the set s sub x if and only if xi minus xj square is equal to 1. So an edge ij is cut by s sub x if and only if xi minus xj square is equal to 1. That's easy to see, right? Because for an edge to be cut, one vertex has to be on one side and the other vertex has to be on the other side. So let's say you fix this edge, right? So here xi value is equal to 0, xj value is equal to 1. So you take the difference and you square, and you'll get value 1. Now, if you pick two vertices from this side, both of them are 0, so the difference is 0. So you square them, you get 0. You pick two vertices from this side, both of them are value 1, so the difference gives you value 0. You square them, you get 1, 0. Right? So only for those edges for which value you get 1, those are the things which are being cut. Okay? So the total number of edges which are cut is just the sum over all the edges of xi minus xj square. Right? Just follows from what we said in the previous line, right? This is 1 if and only if the edge is cut. So if you sum this over all edges, that is the value that is the number of edges which are being cut. Okay? Yeah, so another way to formulate the maximum cut problem is you want to maximize over all vertices of the hypercube of this quantity. Right? Does that make sense? So because each string here corresponds to a cut, right? And then this value here is the number of edges which are being cut by that set. So if you're maximizing over all of these things, so that gives you the number of edges which are cut. Okay? So if you want to prove that the max cut value is less than or equal to k, so the max cut value is less than or equal to k if and only if this polynomial, k minus this polynomial which represents the number of edges cut, that is non-negative over the hypercube. Right? Right? Because if the maximum value of this is less than or equal to k, then k minus this value will always be non-negative. So proving that the max cut is at most something is equivalent to proving that this polynomial is always non-negative over the hypercube. Okay? Does that make sense? So, yeah, so in particular, what we are saying is that if you can prove that this polynomial is non-negative over the hypercube for some particular value of k, then you can indeed solve the max cut problem. Why is that? Because in some sense, you basically want to find the smallest k for which this polynomial is non-negative. And the smallest k for which this polynomial is non-negative would be equal to the max cut value. Right? And so if you sort of have an algorithm to prove this, that this polynomial, if you have an algorithm to prove that this polynomial is non-negative over the hypercube, you can just try out all possible values of k, right? First, you start with k equals to 0. Is this polynomial non-negative? If the answer turned out to be yes, then that is what you output. Otherwise, you try the next one, k equals to 1, right? And then k equals to 2. And you can do this so on. And overall, you will need to try how many values of k? How many? Okay, sure, you can do that as well. But if you do the trivial way of trying all of them, it will be m, right? M is the number of edges. Oh, but since we are only at this point interested in polynomial time algorithms, if you're repeating this process m times, number of edges times, your running time only blows up by a factor of m, which is okay. Okay, but again, the question is, how do you prove that this polynomial is non-negative when k is equal to the max cut value? Yeah, so it's unlikely that we'll be able to prove that this polynomial is non-negative for k equal to the max cut value, because if we can do that, or if we can get a low degree SOS proof of that, then that will imply a polynomial time algorithm for the max cut problem. Right? But since we know that the max cut problem is NP hard, it's unlikely that we can prove this for k equals to the max cut value. Right? So k will have to be something larger than the max cut value. We'll come to that a little bit later if we have time and see what we can say. Any questions? Okay, let's look at one more example of how do we formulate a problem as a polynomial formulation. Okay, so let's look at the maximum independent set problem. We only want to prove non-negativity over the hypercube. We don't want. Yeah, exactly. Yeah, so that's the point. Because over the set of real numbers, it's much harder. So the hope is if you restrict your domain, perhaps there are better, lower degree as first proofs. And for theoretical computer science, these are the ones that we care about. We don't need to prove it over the entire set of real numbers. So this is the only domain we are caring about. So we are asking, can we do better over the smaller domain? Okay, maximum independent set problem. So here the problem is you are given a set of vertices. So you're given a graph. You want to compute the largest set of vertices such that they do not contain any edges. That's called an independent set. So how do we formulate this as a polynomial optimization problem? So again, we'll start similar in a way similar to what we did in the previous problem. So for each vertex, we'll introduce a Boolean variable xi. Right. So again, the same intuition as before. Xi equals to 1 means it's sort of in the independent set. And if it's 0, that means it's not in the independent set. Okay. So here it's a little different from the previous problem because we sort of have a hard constraint, right? That you cannot add any edges inside your independent set. Right. So we not only need to prove non-negativity of polynomials, we need to prove non-negativity subject to a certain constraints, a set of constraints, right? So we're going to add constraints for each edge that xi dot xj is going to be equal to 0. Okay. So this will imply that at least a set of solution, any feasible solution which satisfies all of these things has to be an independent set, right? Because we're saying, okay, values xi can only take value 0 or 1. So if xi xj is equal to 0, that means at least one of these variables has to be value 0. Okay. So if you take the set of vertices which have value xi equal to 1, that will be an independent set because there cannot be any edge in there. Okay. And since we want to compute the, yeah, okay. So if you take the set of vertices which have value 1, then that will be an independent set. And since you want to compute the largest independent set, we would like to maximize this value, summation xi square, subject to these constraints. Okay. That xi xj is equal to 0, what we said here, and that the xi's can only take Boolean values. Sure, yeah, sure. Xi into 1 minus, no, xi into 1 minus xj, if xi is 0, then you're not getting 1, right? Yeah, for the cut problem, what are you saying? Xi into 1 minus xj. So if xi is 0 and xj is 1, you're only getting 0, right? Whereas you should want 1. You can represent it as absolute value of xi minus xj, I guess. But yeah, absolute value will work, but eventually the goal is to get sums of squares of proofs. So it'll turn out later that absolute values are a little hard to work with. Yeah, for the integer program, it's fine, but what you're going to do later, squares help. And the same is the answer to your question as well. Squares will help later on. Yeah, at this level, you can put xi, but xi square will help. Right, but yeah, so that's what I'm saying. What you're saying right now is correct. For this, you can put xi. But eventually, we want to come up with an SOS proof for this, right? So we are going to do something else where the x square will turn out useful. We'll come to that later. Okay. Okay, good. So the maximum independent set is k. Again, if and only if this polynomial, sorry, k minus xi square, summation xi square, is non-negative over the hypercube, subject to these axioms, right? But these are called axioms. So here it's a slightly more general problem. You not only need to prove non-negativity, but you need to prove non-negativity subject to certain axioms. And this is where the positive challenge starts version that we saw comes in useful, right? Because if you remember, there were constraints, right? Didn't have just one polynomial. You were allowed to have multiple sets of polynomials, and you wanted to find one which sort of simultaneously satisfied all of them, right? So all of these constraints can now be encoded in that positive Stellensatz framework, right? So I'm not going to go into the details, but essentially you can sort of, the positive Stellensatz framework lets us handle these kinds of constraints as well. So we want this set to be an independent set, right? So how we need to encode that somehow, right? So what does an independent set mean? It should not, the set of vertices which have value x1, they should not contain any edges. Okay, so how do you enforce that? If you can guarantee that xi is equal to 0 for all edges, then the set of vertices which have value 1, they will be an independent set, right? Because if there was an edge between them, then xi xj for that edge would be equal to 1, right? But since you're enforcing this, within the set of vertices which have value 1, there cannot be any edges, right? So this is one way of encoding independent sets. Okay, so I hope I have convinced you that at least optimizing, we're proving non-negativity of polynomials over the hypercube is also very interesting in these kinds of like computational problems, theoretical computer science problems. Okay. Okay, so now to come to your question. So what kind of upper bounds can we prove on the degree of the SOS proofs? So at least if you're restricting yourself to polynomial over the hypercube over here, you can prove that every non-negative f has a 2n degree SOS proof. So the proof of this is very simple. It will contain in one slide. So we're going to prove this theorem. No, I'm saying this is for any f, not just the ones we saw earlier. Yeah, for every non-negative function over the hypercube has a degree 2n SOS proof. So why is that? So let's assume that the function f is non-negative over the hypercube. Okay, so we define the function g to be square root of f. Okay. So clearly f is equal to g square. So if we can prove that g defined in this way has degree at most n, then that solves our problem. Right? So now this is a general theorem that for any function over any polynomial over the hypercube, you can write it as a polynomial of degree at most n. Right? So let's look at this expression over here. So I claim that g can be any function over the hypercube is equal to this expansion. Okay. So let's parse this. So you're summing over all y over the hypercube of gy times this term here. All right. So this is product over all those indices where y is equal to 1 of xi, and product over all those indices where y is equal to 0 of 1 minus xi. So the way it's written, it says that it ensures that this product is not equal to 0, only when y is equal to x. Right, so let's look at that. So when y is indeed equal to x, so what do you get? So y is equal to 1. So all of these terms contribute 1. And when y is equal to 0, then xi is also equal to 0. So all of these terms also contribute to 1. So if you look at this product, you get value 1. Now let's say y is not equal to x. That means there is some coordinate I for which yi is not equal to xi. Right? So now let's look at the yi. Is that yi plus a 1 coordinate or a 0 coordinate? If that y is a 1 coordinate, then if you look at the corresponding term here, you'll get 0 for the corresponding xi. Right? So then this whole product becomes 0. Now if the ith coordinate where they differ is value 0, then if you look at this term here, xi is 1. So 1 minus xi is 0. This whole product becomes 0. Right? So this product is equal to 1 when y is equal to x and 0 otherwise. Okay, so when y is equal to x, this value that you get is actually g of x, right? Therefore, it's equal to that. Okay? So this is true for any polynomial over the hypercube. Any polynomial over the hypercube has degree at most n. And that's what this proof is saying. Wait, why is this degree at most n? Okay, so if you look at each of these terms, right? So yeah, so because you're multiplying like n linear terms here, right? So some number of terms here, some number of terms here. So multiplying n linear terms, so the product can have degree at most n. Okay. So we have f is equal to g square, where g has degree at most n. Therefore, this f is equal to g square has degree at most 2n, right? Because it's a square of a polynomial. Does that make sense? Right. So at least what this is saying is that one can compute SOS proofs in exponential time, right? Because at least over the hypercube, uh, every non-negative polynomial has a degree 2n proof. So at least using this black box SOS algorithm, SDP algorithm, you can compute these things in exponential time. Right. So the same thing can also be specialized to work over this. Yeah, I'm skipping all those details. It's yeah. In particular, one can add axioms, right? Like I said, you can add xi square equal to xi kind of constraints, right? So even if you optimize over real numbers, if you add xi square equal to xi, it'll ensure that these are, Boolean values. Okay. So in general, yeah. So the summary is that of this slide is that every SOS, every polynomial over the hypercube has a degree 2n SOS proof. Therefore, in exponential time, you can prove you can compute non-negativity. Right. But again, in polynomial time, we want efficient algorithms, right? Yeah, so this is what we said. In exponential time, you can, given any polynomial over the hypercube, either decide whether it's greater than or equal to 0 over the hypercube, or prove whether that there exists some x so that fx less than 0. Right? And so, but again, like I said earlier, this is NP hard in general, right? Because as we saw earlier, this is the polynomial that encodes a max cut problem. So if we can actually do this in polynomial time, then that will give us a efficient algorithm for max cut, which is unlikely to happen. So in general, we cannot prove this for, or at least we do not hope to prove this for general polynomials. Right? So maybe we need to refine our goal. So what do we actually want to do? Okay. So let us fix some degree constraint that we have. Let's say some arbitrary constant d. So the goal that you would like to do is either compute a degree d certificate, SOS certificate that fx is greater than or equal to 0 over the hypercube, or output a collection of points that pretends to be a point such that fx is less than 0. Right? We'll formalize what all this means, what pretends to be means. Right? But in some sense, is the goal clear? That is sort of the best we can hope for, right? Because we are saying we are fixing some number d. We only want to restrict ourselves to degree d SOS proofs. Why is that? Because degree d SOS proofs you can compute in time n to the d. So if d is some small constant like 5 or 10 or whatever, that will give you a polynomial time algorithm. So we have fixed the running time. Now we are asking either compute a degree d SOS proof. Ideally, we would like either compute a degree d SOS proof or compute some x such that fx is less than or equal to 0. Right, but again, since it's NP hard in general, that is something that we cannot hope to do. So in some sense, the best we can hope to do is either compute a degree d SOS proof or output something that pretends to be a point such that fx is less than or equal to 0. Right? So we need to formalize what that second point means. Okay, any questions to this point? I have 10 minutes. Okay. Okay, so is it clear what you're trying to do here? Okay. So the first observation is that degree d SOS proofs of non-negativity form a cone. So what does a cone mean? So cone is just a convex set which satisfies like two properties, that if you sum 2 points from the cone, it should lie in the point. And if you take any point in the cone, multiply it by some positive number, that should still lie inside the cone. Right? So these are the two things that a cone needs to satisfy. So then one can verify that degree d SOS proofs do satisfy this, right? Because if you take two degree d SOS polynomials, you add them, it will still be a degree d SOS polynomial, right? you take some degree d SOS polynomial multiplied by a positive number, it will still be a degree d SOS polynomial, right? So the degree d SOS polynomials, they form a cone. Because I've tried to represent it in 2 dimensions, but it's actually some very high dimensional object. Okay. And yeah, so the good thing about cones is that they satisfy this kind of a separation theorem. So what does that mean? So suppose you have a polynomial for which there is no degree d SOS proof, right? So then using some fundamental theorems from convex geometry, you can prove that there exists a hyperplane that passes through the origin that separates this point from the cone. So the proof is sort of by picture, right? Because if this is your cone, this is your F, you can always find a line that passes through the origin which separates this, right? So this is a proof by picture, if you will, right? Okay, so you can always find a hyperplane passing through the origin that separates the polynomial from the cone. Okay, so note that if you do not have a cone here, then this is, if you just have a convex set instead of a cone, then this is not true, right? You can find a hyperplane, but you cannot guarantee that the hyperplane is not passing through the origin. Is there a chalk or something? Maybe I can, right? So, right, so let's say this is the origin, right? And you are given some sort of a convex set here. And you here, this is your point F here, right? So there is no hyperplane passing through the origin that separates this, right? You can always find a hyperplane, but it will not pass through the origin. So you really need the cone property here. And it's really helpful that the cone is, yeah, so the degree d SOS proofs do form a cone. Okay, so let's say so we are going to focus on this hyperplane, right? This separation hyperplane and see what it tells us. Right, so so typically for a hyperplane, we represent it by its normal to the hyperplane. So let us assume just by scaling that summation over x of this mu x is equal to 1. Right, scaling this does not change the hyperplane, right? Because it's passing through the origin anyway. And yeah, so then this half space, the half space above this red line is given by this set, right? All those points G says that summation over x mu x gx is greater than or equal to 0, right? And so this is the half space which contains all the degree d SOS proofs, right? So the degree d SOS proofs are contained in H, and the F is on the other side of the hyperplane, right? So what this implies is that summation over x of mu x fx is strictly less than 0, right? That makes sense. So till this point, this just follows from the definition of the separating hyperplane, right? Nothing fancy happened till now. Right. Okay. So now if we got lucky and this mu satisfied this property that all the entries were indeed non-negative, okay, so then we can think of the mu as a probability distribution, right? Because it's, suppose we got lucky and all of them are non-negative. We also have that summation mu x is equal to 1. So then that's like a probability distribution of the vertices of the hypercube, right? And so this constraint that we had, or this implication that we had, summation over x of mu x fx less than 0, that actually implies that there exists an x point such that fx is strictly less than 0, right? Again, all of this holds only if we really got lucky and all the mu's were non-negative, right? So then we can actually solve the best case scenario that we hoped for. Yeah, exactly, right? So this is like the expected value of fx is negative. So if the expected value of a random variable is negative, then it has to take a negative value on at least one of the points, right? That's sort of what we are saying, right? Because suppose fx was always greater than or equal to 0, mu x is always greater than or equal to 0, so then the product has to be greater than or equal to 0, right? So all of them cannot be greater than or equal to 0. Mu x is the, sorry, can you say again? So f is like a function, right? It's putting values over the hypercube. And mu is a probability distribution, right? It's putting mass over the vertices of the hypercube. Yeah. Yeah, so mu is a probability distribution. F is some set of values. Yeah, you can think of it as a random variable as well. Yeah, so all we're saying is that if a random variable has expected value negative, then at least it has to take negative value with positive probability over the discrete setting, not in general. Okay, but of course, in general, this needn't be true, right? Because firstly, if it were true, we would have proved a best case scenario, which is unlikely to be true. So in general, nu needn't be a non-negative function, and therefore it's not a probability distribution in general. Okay, but we can still sort of pretend that it's a probability distribution and try to work with it. Right, so let's say we define the pseudo expectation of a function to be this value, right? Summation over x in 0, 1 to the n of mu x fx, right? So in some sense, it's the formal expectation. It's mu is not a probability distribution, but it's still, we are defining expectation with respect to mu in this way, right? So it's not an expectation, so we are going to call it a pseudo expectation, right? And this mu, we'll call it a pseudo distribution or a degree d pseudo distribution more formally, if it satisfies these two properties, right? That for every polynomial of degree at most d over 2, its pseudo expectation of x square should be non-negative. And the pseudo expectation of 1, which should be 1, which is just a normalization constraint, right? So if you recall, what we saw 2 slides ago, the mu that we got is indeed a pseudo distribution, right? Because it satisfies these two properties, right? So the first thing we did was we normalized the mu such that summation over mu is equal to 1, right? So that gives us the second property, right? Because what is the expectation of 1? If you plug in 1 over here, so expectation of 1 is just summation over mu. So the first thing we did 2 slides ago was normalize this so that expectation of 1 is equal to 1. So we have that. And the second thing we did was, so let me just go back. Yeah, so we normalize this thing over here. So this gives us that the pseudo expectation of 1 is equal to 1. And the second thing we did was we showed that the degree d SOS proofs are contained in H, right? So that means for any polynomial which is the degree d SOS proof, mu x gx is greater than or equal to 0, right? So that means the degree d SOS. So this is like the formal expectation, pseudo expectation of G. So what this is saying is that the pseudo expectation of every degree d SOS proof is non-negative. Okay, so what we get from here is not a distribution, but we are getting a pseudo distribution. Using SDPs, yes. Okay, so the point is that you can pretend that the pseudo expectation operator behaves like an expectation operator as long as you are evaluating it only over sum of squares polynomials of degree at most d. Okay, so you can make all sorts of arguments or proofs that you want that only involve sum of squares proofs polynomials of degree at most d, and then you can pretend that the pseudo expectation operator is really just the expectation operator, right? So essentially that's what this is saying. Okay, so any questions to this point? Right, okay. So to summarize what we said, or 2 slides ago, so every function f and for every degree d, so there exists a degree d SOS certificate if and only if for every degree d pseudo distribution satisfies the pseudo expectation of f is greater than or equal to 0. This again you can prove by this picture, right? Because if the f does not lie in this cone, you can always find a separating hyperplane, and that will give you a pseudo distribution for which the expectation is strictly less than 0. Right? So yeah, so whereas if the polynomial f lies inside, then for whatever hyperplane you take, it has to be non-negative, right? So then you cannot separate this. So that's essentially the proof of this theorem. Okay, so this degree d SOS proofs and this pseudo distribution, they go hand in hand. They are sort of like duals of each other. So and often, so while degree d SOS proofs are used to prove non-negativity, so the pseudo distribution sort of give you the negation of that, right? So if you want to prove that the polynomial is not non-negative, or if you want to prove that the polynomial takes some negative value somewhere, then the pseudo distribution operator view comes in more useful, right? And that is especially useful in theoretical computer science because you are trying to either often optimize something or like minimize something or maximize something. So there the pseudo distribution view comes in useful. But again, given that these things are duals of each other, the algorithms for computing the two of them are essentially the same, right? So if you compute like so the same algorithm, the semi-definite programming algorithm that one can use for computing SO certificates, it's like if you solve the dual of that, so that will give you the pseudo distribution operator for these things. Yeah, I'm not going to go into too much details about this because that'll be a major detour. But again, yeah, if you're interested more in this, I'll be happy to talk more offline about what semi-definite programming is and what all this Lagrangian duality is and all those things. Okay. Yeah. You can essentially do it that way. Yeah. I mean, sort of. Yeah, sure. You can sort of say the answer is yes. Yes. Okay. Any other questions, comments? I clearly overestimated how much I can talk. How much time? 12:30 using. Okay. Okay. So okay. So at least I'll try to at least mention one application of all of these things. So these things are often used in theoretical computer science in designing approximation algorithms, right? So what do we mean by approximation algorithms? So let's take the example of the max cut problem. So as we said, it's NP hard in general. So we do not really hope to solve it exactly in polynomial time, right? So there, then we try to get an alpha approximation algorithm. So what does that mean? So when we say that an algorithm is an alpha approximation algorithm for the max cut problem, if the algorithm finds a solution whose cost here is the number of edges cut, is at least alpha times the cost of the optimal solution for every instance. If your algorithm comes with such a guarantee, we'll say that it's an alpha approximation algorithm. Ideally, we would like alpha equal to 1 because that means you're always getting the optimal algorithm. But again, that's unlikely because that would be saying that you're finding the optimal solution for NP hard problems. Right, so the goal is to design algorithms for which alpha is as close to 1 as possible. Right, so again, I'll try to sketch a little bit about how you can use these things for the max cut problem. So firstly, let's look at a trivial algorithm for max cut, which gives us a half approximation. Right, so recall in the max cut, you want to pick a set of vertices S so as to maximize the number of edges that go from S to V minus S. So let's just take a random partition algorithm, okay? So that means you just pick each vertex independently with probability half. Right, so what is the expected number of edges that you're going to cut? Okay, so let's maybe break it down a little bit. So what is the probability that an edge is cut, right? Fix an edge UV. Huh? Yeah. Yeah, so the probability that an edge UV is cut is either U is in S and V is not in S, or V is in S and U is not in S, right? So the probability of that is half times half plus half times half. That gives you half. So the expected number of edges which are cut is at least half the number of edges. Is equal to half the number of edges, right? And that is at least half of the max cut value, right? Because the max cut value is at most the number of edges, right? If there are m edges, you cannot cut more than m edges, right? So the max cut value is always less than equal to total number of edges, right? So this E over 2 is at least half times the optimum value, right? So the simple algorithm gives you a half approximation. Now using all the sum of squares methods, we can do significantly better than this, right? So for every graph G, what we can prove is that the max cut value minus this 0.878 times this polynomial, the max cut polynomial over here, which we saw earlier, has a degree 2 SOS proof. Okay, so this was like a breakthrough result by Gomez and Williamson from 1994. Okay, so for every graph, the K that we are plugging in is what is the max cut value. So what you're saying is max cut minus some scaling value, 0.878 times this f of g has a degree 2 SOS proof. Okay, so firstly note that it's a polynomial time algorithm, right? Because the degree we are using is only 2. So the running time is n to the d, which is some polynomial. So this essentially implies that there is a 0.878 approximation algorithm for the max cut problem. Well, this seems like a seemingly arbitrary number. Uh, it surprisingly turns out that you cannot do better than this, whatever this arbitrary 0.878 is. So there's a certain conjecture called the unique games conjecture, which implies that assuming that conjecture, you cannot improve upon this 0.878 kind of a arbitrary constant. Okay, so at least I'll tell you the algorithm and then sketch of the analysis. Okay, so what we're going to do is that you're going to solve the SDP for the max cut polynomial, and that will give you a degree 2 pseudo distribution, right? So let mu be this pseudo distribution that you get over the hypercube. What we're going to do is that prove that there exists a distribution mu prime over the hypercube, where mu prime is a real distribution, not a pseudo distribution, such that the expected value of this cut polynomial, fg, so did I put it here? Okay. So fg is this polynomial, okay? So the summation over edges ij in E of xi minus xj square. Okay, so the expectation over this real distribution of fg is at least 0.878 times the pseudo expectation of fg. Okay, so I'll not maybe give you the full proof, but at least the hope is that I'll give you a flavor of what the algorithm looks like. Okay, so the first step is you're going to sample a Gaussian vector with mean equal to the pseudo expectation of x, and with covariance equal to the pseudo expectation of x transpose. So there are some standard algorithms where you can do this. And once you sample such a Gaussian vector, then the algorithm is very simple. You just output the vector x, where xi prime is equal to 0 if gi is less than half, and 1 otherwise. Okay, so this distribution that you get from here is what we are going to call mu prime. Okay, and what we can show is that the expectation over mu prime of this cut polynomial is at least 0.878 times the pseudo expectation of this polynomial. Right? Yes, yes. So gi is the ith component of this vector. Yeah. I mean, yeah. So the okay, yeah. So why are we choosing half? Because so in some sense, you can prove that the pseudo expectation of x has to be equal to half, right? Because it's like for any solution, either you put 0, 1 or 1, 0, they're symmetric. So it's like in some sense, this value is really equal to half on all the coordinates. So we shouldn't be looking at that. And so, yeah, so, sorry. So can you say it again? No, x is a variable, right? So mu is a pseudo distribution over degree 2 polynomials, right? X is a vector. X is a vector. Okay, so what is mu, right? So mu is a pseudo distribution over vertices of the hypercube, right? So it's like giving you a value mu x, right? For every value x on the hypercube. So this is a matrix, right? So this is summation over mu x of xx transpose. So when we say pseudo distribution over mu of xx transpose, what we mean is summation over x in 0, 1 to the n of mu x times xx transpose. Okay, so that's what that means. Okay. Right, and this is a pseudo distribution over degree 2 polynomials, right? So you have all those moments. Okay, so is the algorithm clear? Yeah, so I don't want to get too much into the analysis. I guess I only have 5 minutes. I might not make a lot of sense. So essentially, the idea is that you sort of take this matrix and then you factorize them, right? So you can show that is a PSD matrix. So you factorize them and then you get vectors. So then this whole algorithm, you can view it in a geometric way, where VIs are the vectors that you get from factorizing that matrix. And you're basically asking that if you take a random sample. Sorry, you have a question? Right. So what I meant by that is, so it's a PSD matrix, right? Um, so for any PSD matrix P, you can factorize it as V transpose V. Okay, so it's for any PSD matrix. And so when I say factorize into vectors, I mean where I mean by Vi is the ith column of V. Right, so that's what I mean by factorize into vectors. Okay, so for any PSD matrix, you can factorize into V transpose V, which are matrices, and Vi is the ith column of V. Thank you. Yeah, so roughly, so let me just, so roughly you can view this as saying you take that matrix and then you factorize it, you get these vectors. And it comes down to bounding the certain kind of a quantity here, right? This value here, infimum over this value. It's really a very geometric proof. If you do all this, it turns out that that value is equal to 0.878. And that's where the 0.878 is coming from. Okay. Yeah, so in the interest of time, I'll not go into more details about this. But yeah, let me finish by saying that what I gave was just like maybe one application of all the sum of squares polynomials, but it's really being studied not just in theoretical computer science, but in like real algebraic geometry, optimization, control theory, and many, many areas, especially in the last 2 decades where there have been many new results in approximation algorithms, quantum information theory, game theory, combinatorics, and many, many others, right? And again, a lot of these computational questions have really been studied in the last 2 decades. There have been many new algorithms, some amount of lower bounds, but it seems like the power and limitations of these things are yet to be fully understood, right? So it's like a very, very active area of research in theoretical computer science. And yeah, so if you have any questions, I'd be happy to answer them now or during the break. And I guess that's all I had planned. So yeah, thank you for your attention. Any questions? Yeah, okay, so what does semi-definite programming mean? So it's like a special case of convex optimization, right? So, okay, so in general, what does optimization mean? You are given some function that you would like to minimize or maximize subject to some constraints, right? So convex optimize, yeah, so in general, these things are NP hard, right? If you're just given some arbitrary optimization problem. So convex optimization is when the function that you're trying to optimize or minimize is a convex function. And the constraints, the feasible set of solutions is also a convex set, right? So in such cases, it sort of turns out, okay, if you have one or two other technical conditions, that you can actually get polynomial time algorithms for convex optimization, okay? And so semi-definite programming is a special case of convex optimization, where it looks like you are optimizing your set of solutions over a set of matrices which are positive semi-definite. Okay. So the set of positive semi-definite matrices, one can show that is a convex set. Right? That's very easy to show. Just comes from, yeah, there are many ways to show that. Yeah, so optimizing over the set of positive semi-definite matrices subject to some other constraints is what is known as semi-definite programming. And again, the reason is that why it's useful is that you also have this geometric view, right? Because if your solution is optimizing over positive semi-definite matrices, you get a matrix like this. You can factorize it into vectors. And then when you work with these vectors, that gives you like a geometric view of many of these things, right? So for that reason, semi-definite programming is also viewed in the probabilistic sense, in the pseudo distribution sense, and also in the geometric sense when you factorize those things and look at the vectors. Yeah. Exactly, yeah. So pretty much most semi-definite programming algorithms look like linear programming plus one constraint that a certain matrix is PSD, right? So yeah. What is it? No, there's even there, it depends on the degree, right? It's not a polynomial time algorithm. So it's exponential in the degree, yeah. So if the degree is fixed, sure, it's polynomial. Integer programming is exponential time in general, yes. Mhm. Yes, I think maybe I didn't say that clearly. So the even over the hypercube, the running time is still exponential in the degree. So the hope is that maybe if you restrict yourself to hypercube, maybe lower values of d will suffice, right? That was the hope, yeah. And as we saw in the max cut case, right, degree 2 sort of helps for a slightly larger value of k than the max cut. But essentially degree 2 works, right? You don't need to go to degree n. There's one other question here. Yes, sir. What's a PSD matrix? So there are many ways of equivalent ways of writing this. So we say a matrix is PSD. First, let's say it's a okay. So let's say it's a symmetric matrix. So we say a matrix is symmetric. Yes. So we say a matrix is symmetric if P is equal to P transpose. Okay. So a symmetric matrix is said to be PSD if all its eigenvalues are non-negative. Is there a follow-up question? Okay, so we say P is PSD if this is the notation. There are many equivalent definitions. So this is PSD if all its eigenvalues are negative, non-negative. That's one condition. One equivalent, yeah, another equivalent formulation is that okay, good. So if you're looking at symmetric matrices, you can show that all its eigenvalues are indeed real. Okay, you can write PSD matrices for complex matrices as well, but everything I talked about here is primarily only for real matrices. Yeah, so that's one condition. Another equivalent condition is X transpose Px is greater than or equal to 0 for all X in Rn. Right, and there are a few other such constraints which are equivalent formulations of PSD matrices. Right, and yeah. Yeah, so it turns out specifically in all these SOS proofs, PSD matrices come up a lot. If you look inside this algorithm to, or SDP algorithm for solving this PSD matrices, so for these SOS proofs, PSD matrices come up a lot. And yeah, so okay, so yeah, so maybe another homework exercise is to show that the set of all n cross n PSD matrices forms a convex set. Okay, so you can try to prove that you can use one of these definitions and you should be able to get that. Yeah, so convex set as in geometrically, right? So we say that K subset of R to the n is convex. If you look at any two points inside K, the entire line segment joining them should also be inside K, right? So it's convex if, say for A comma B in K, we have lambda A plus 1 minus lambda B in K, right? For all lambda in 0 comma 1. Right, so it's a, yeah, so the generalization of convexity to higher dimensions, right? So for any A comma B in K, you look at the line segment joining A and B, right? So that's given by lambda times A plus 1 minus lambda times B for all lambda in the range 0 to 1. So that entire line segment should be contained inside K, right? So if that holds, then we say it's a convex set. Okay, yeah, so using this definition of convexity and using these definitions, we can try to prove that the set of all PSD matrices is indeed a convex set. Any other questions? What's a Gaussian vector? Okay, so what is a, okay, let me do this in one dimension. So what is a normal random variable, right? So we say that X is a normal random variable with denoted by this with mean mu and variance sigma square. Um, if it's PDF, the probability distribution function is given by e to the minus x minus mu square divided by 2 sigma square. Right. Yeah, so the Gaussian vector is maybe a high dimensional analog of this. Again, it sort of comes up very naturally in many places. Again, I'll be able to answer more questions offline, but from a normal distribution. But here we were looking at something a little bit more, that we were specifying the correlations between them as well, right? Because every pairwise correlations we said should be the pseudo expectation of XX transpose. Okay, thank you.